In our today's lecture, we are going to study topic number 6, equipotential surfaces. Now we know that for a single charge, the potential at distance r is given by V is equal to K Q by R, where K is equal to 1 upon 4 pi epsilon naught. So here also in this figure, due to this single charge at this distance, suppose r, the potential will be this much. But we know that around this charge q, we can get such many points having same distance. We get infinite points with such distance, and so the potential at those points will be same. So this type of surface having same potential are called equipotential surfaces. So here in 2 dimension, all those points are found to be on a circular path, but actually in 3 dimension at distance r with charge at the center, you will find that as a spherical surface. And so a spherical surface at for which the charge is at its center with radius r, that spherical surface is an equipotential surface. Again, if we take less distance from this charge q, then once again we will get infinite points with the same distance on the spherical surface. So even on that surface, the potential is same. So even that surface with less distance or less radius is also an equipotential surface. The difference is that for that larger radius, the equipotential surface has less potential, but for this smaller radius surface, the potential is more. So it is clear that with charge at the center, we get such infinite equipotential surfaces. Also, for a single charge, we know that the electric field is radial coming outward, and at any distance from the charge q, we get the equipotential surface, and you can see that on such equipotential surface at any point, the electric field is always normal to the surface. Here the surface is spherical, so you can easily find that at that point the electric field is normal to the surface, but this is applicable to any kind of equipotential surface. In next figure, the electric field lines due to a uniformly charged plane surface is given. Suppose this is a plane surface having uniform charge density, and we know that due to such surface the electric field lines, they are parallel to each other. So if the electric field lines are parallel, then we get the equipotential surfaces as a plane figure or a plane sheets. So you can see that this is an equipotential surface, even this is an equipotential surface, even this is an equipotential surface, and we can get such infinite equipotential surface. But here the shape of that surface is a plane because the electric field lines are parallel to each other. Earlier we have seen for a point charge, and for such point charge the equipotential surface was spherical in nature. Here you can see it is spherical, but for this type of situation the equipotential surface is a plane surface. Once again, in the direction of electric field, the potential of this surface will be more, but the potential of this surface will be less. Still, if we move in the direction of electric field, and if we take the upcoming surfaces, then potential for that surfaces will go on decreasing. But on the same surface at any point, the potential is same. Also, for this type of system of charge, you can see here the positive charge and a negative charge is kept close to it. So here also the equipotential surface is like this. You can easily see that here these circles are not concentric and not exact radius at both the side, because there is an effect of negative charge over this surface also. And so the equipotential surface, when such two charges are kept closer, is like this. Even when the two positive charges are kept closer to each other, then for this charge also the equipotential surface near to it will be circular, but as we increase the distance, finally we can find the equipotential surface due to both these charges will be in this way. So this is only for the information, no need to remember it. Our next topic is 2.6.1, relation between field and potential. Means we have to obtain the formula which relates electric field E and potential V. Now here the method given to explain this is not that much simple. So I'll show you one good method by which you can easily understand it. One more thing, this cannot be asked as a theory, but the final formula, that is very important. Even the earlier topic which we have seen, this about equipotential surface, even that is also for MCQ. This cannot be asked in the form of theory. Now in figure, a uniform electric field is shown in the upward direction, and two equipotential surfaces A and B, which are normal to the electric field, are shown. Now potential at any point on the surface A will be same. That means each and every point on this surface, the potential will be same, and let that potential is denoted by VA. Similarly, potential on this surface at any point will also be same. Let us denote the potential of this surface be VB. Now, as we have studied earlier, that if I'll move a unit positive charge from this point P towards this point O, then the work is required to be done. So here also, let us consider a unit positive charge is moved from the equipotential surface B towards equipotential surface A. In that case, the work done is given by WBA negative of integration B to A E dot dl. Students, this is not new formula. We have already studied this. And so, this work done on a unit charge is nothing but the potential difference between points A and B, and hence VA minus VB is equal to this, which is same as the work done on a unit charge. Now here the difference between the potential is given, and so if we consider a very small difference, then we use dV. If the large difference is considered, then we use delta V. But here if we consider a very small displacement, then the symbol used is dV. And so here also, as electric field is constant, it is as it is, but displacement should be considered very small, because for very small displacement the change in potential is also very small. Also, here there is a dot product between these two, but electric field and displacement, they are in same direction, and so we have removed dot product. Finally, in this equation, making the subject E, we will get E is equal to minus dV by dl. So this is an important formula which you should remember. Now in short form, if you want to remember this formula, then you can remember this in the form of V is equal to minus ED. Now next topic is about potential energy of a system of charges. Now if only one charge is present, then we say that there is an electric field around it in all the direction. But if I say there is a charge Q1, and if I place a charge Q2 around it at some distance r, then we know that to put this charge Q2 in the electric field of charge Q1, we need to do some work, and work done on this charge in the electric field of this charge Q1 gets stored in the form of potential energy, and that potential energy is always due to the system of two charge particles. Once again students, if I'll put this charge here, and then if I have to place this charge at this point B, then I have to bring this charge Q2 from somewhere. Somewhere means, suppose I am bringing this charge from infinity to this point B. So in that case, actually there is an electric field around this charge. So I have to do the work against the electric field during the motion of this charge or the displacement of this charge, and that work done is stored in the form of potential energy. In another way, we can also imagine that suppose we have already kept charge Q2 and now we want to place this charge Q1 at this point. So once again we have to bring this charge Q1 from infinity to this point, and when we are displacing this charge Q1 towards point A, it is moving in the electric field of charge Q2. So definitely we need to do the work. So both the methods are similar, and in both the methods the work done will be same, and that work done is stored in the form of potential energy of the system of two charged particles Q1 and Q2, which are separated by distance r1, 2. Now students, one more thing to remember is potential energy is a scalar quantity. So here direction is not important. So we have not kept vector over this r1, 2. So if I write this r1, 2 or r2, 1, meaning is same. Finally, the formula for the potential energy U is equal to K, product of the two charge, upon distance between them, where K is equal to 1 upon 4 pi epsilon naught. So this is a very simple formula. We know that if the two charge particles, they are separated by distance r, then the force acting between these charges Q1 and Q2 is given by F is equal to K Q1 Q2 upon R square. So here also you can see the similarity between this formula of potential energy and this formula for the force. If we remove square here, then it becomes the formula for the potential energy, and if there is a square, then it is the formula of force. Also about electric field and potential. Electric field and the potential is related to only single charge. So here if I put any charge Q and at distance r, if I choose point P, then at this point P there is an electric field due to this charge, which is given by E is equal to K Q by R square. But if I say what is the potential at point P due to charge Q, then we know that we have to simply remove this R, and so the formula will be K Q by R for potential. So remember students, if a single charge is there, then around it we have electric field, and at any point in that electric field there is a potential. But if there are two charges, then between the two charge there is a force acting between them, as well as there is a potential energy for the system of that two charges. Again, here I have written U12 is equal to this. But in place of U12, if I write U21, then also it is same as U12. So here the potential energy of the system of two charge particle is obtained. Now what happens if there are three charge particles? Here you can see there are three charge particles Q1, Q2 and Q3. Distance between Q1 and Q2 is given, that is R12. Distance between Q2 and Q3 is R23, and distance between Q1 and Q3 is R13. Now here there are three possible pairs between the two charges. One possible pair is for Q1 and Q2, and for this system of two charges we get the potential energy U12. Similarly, the other possible pair is Q2 and Q3. So even for this two system of charge particle also we have potential energy U23, and the last possible pair is Q1 and Q3. For this system also we get the potential energy. And so finally, to find the potential energy of this system of three charged particles, we use the total potential energy U is equal to the potential energies U12, U23 and U31. And what is U12? That we know, because we have already obtained the formula for this. Similarly, if U23 is there, then in place of 1 2 we can write 2 3, and similar changes we have to make for the charge, and so we get the total potential energy for three charge particles. Now if there are system of more charges, so here I have written the similarly the potential energy of system of n charges. Then for n charges also the method is same. We have to consider here each and every possible pairs. No pair of the two charge should be repeated and no pair should be missed out. And finally, by adding up all that pairs, we can get the resultant or the total potential energy of the system of charge particles. Now this can be better understood by next example. Now example number 2.4. Here a square is given, and on the vertices of this square four charges are placed. So here we can say that it is a system of four charge particles. Now in the first part, that is A, we need to find the potential energy of the system of these four charge particles. So the potential energy or the work done meaning is same. It is because the work done gets stored in the form of potential energy, and so W is equal to U. Now to find the work done, we have to place these charged particles on the vertices. Suppose earlier on this square there are no charged particles, but if I go on placing the charges one by one, then I have to do some work. Suppose if I place the first charge, that is plus q, at the vertex A. Now when I bring this charge plus q, there is nothing around it, and so no work is required to bring this charge particle to point A. But now when I will bring this charge minus q at point B, already the electric field of this charge which is at point A is present around it. So now to bring this charge minus q, I need to do the work, and that work done is stored in the form of potential energy. Now if I'll bring this charge particle plus q at point C, so to bring this charge particle from infinity to this point, the work is required to be done because the electric field of both these charge which are at point A and at point B are present around it. Now after placing this charge particle at point C, finally if I'll put this charge particle at point D, then once again the work is required to bring that charge particle to point D. Finally, this total work done gets stored in the form of total potential energy of the system. So actually this is the process, but here we don't have to remember this process. We have to simply consider the possible pairs. How many possible pairs are there? So there are 6 possible pairs: pair AB, pair BC, pair CD, and pair DA. So these are the 4 pairs which are related to the sides of a square, and the 2 pairs are diagonally opposite to each other. So pair AC and pair BD. So again there are 2 more pairs. So finally in all there are 6 pairs for which we have to find the total potential energy. Now mathematical steps, quite simple. Work done gets stored in the form of potential energy, and this potential energy is related to the each pair. So UAB, UBC, UCD and UDA, which are nothing but the sides of a square, and then the 2 diagonals UAC and UBD. We can now easily find the potential energy of these individual pairs, and then we can add it. Now from the figure it is clear that the potential energy of these 2 charged particles will be U is equal to K Q minus Q. Why minus Q? Because here first charge is plus Q, second charge is negative, so we have to put minus, and distance between them is D, which is already given in the data. So here the potential energy U of A and B is given by this formula. And finally, if we'll make it more simple, then K Q into Q, that is Q square upon distance D, but negative sign is there. Similarly, potential energy between B and C is also same, because this distance is once again D. Once again the product of two charge, one is negative and the other is positive. So potential energy is once again same as the earlier. Potential energy of C and D is also same, because one charge is minus, the other is positive, and the distance is same because it is a square. Also for A and D, the potential energy is same. So I have written here the potential energies UAB, UBC, UCD and UDA are equal only, and that is equal to this. Let us give these equations as number 1 and this as 2. So for the sides it is completed, and we also obtained this. Now for diagonals, you can see for these charges along the diagonal, both are positive, and the distance between these two charge particle can also be obtained using Pythagoras theorem. Because this distance is D, even this is D, then this distance will be root 2D by using Pythagoras theorem. So here the potential energy can be obtained, and that will be positive only, because both the charges are plus. Now if we'll find the potential energy of second diagonal, that is B and D, then here both the charges are negative. So once again minus into minus will become plus. Again the length of the diagonal is same as earlier, that is root 2D. And so potential energy of these two pairs, pair AC and pair BD, is also same. So here I have written the potential energy for the diagonals of a square. UAC is equal to UDB, that is equal to K Q square upon distance root 2D. This was for the sides. Now let us give this equation number 3. Now all these 6 pairs, all these 6 possible pairs are obtained. So from this equation number 2 and from this equation number 3, we will put the values in equation number 1, and then finally we will get the resultant or the total potential energy, which is equal to the total work done. So now look here, after putting the values from 2 and 3, we will get 4 into this, because there are 4 pairs related to sides and their sign is negative, so minus is there. For these diagonals, as there are 2 diagonal, there is 2 here, you can easily do it. And finally applying a simple mathematics, you will get this result. W is equal to minus KQ square upon D in bracket 4 minus root 2. How it is obtained? So you have to simply take out the common from these two terms. What is common? So common is k q square upon d here also, and k q square upon d here also. So that is taken out. Even here minus is taken out common. So first term, in this first term only 4 is remained, and this second term 2 upon root 2 into d. But we know that 2 upon root 2 is equal to root of 2, and so it is there here. And as this is positive and we have taken out common minus, so there is a negative sign. Now students, in your textbook a complicated method is given. Just go through it, but I found this as the simplest. In your textbook, in place of k, 1 upon 4 pi epsilon naught is written. So whenever you use k to make the simple calculation, finally at least you should mention that k is 1 upon 4 pi epsilon naught. So this is the first part. Now in the second part, what we have to do? So it is asked that now we have to bring a charge q naught from infinity to the center of this square. So we know that to bring this charge from infinity towards the center, we need to do some extra work, because already the work is done to set up these charge particles, and again if we are bringing this charge at the center, then an extra work is required. So to find this extra work, what we will do? We will first find the potential at the center. Remember what we are going to find? We are going to find the resultant potential at the center, and then we will bring this charge q naught, because u is equal to a charge into potential. So first we will find the potential V at this point E, which is at the center of the square, and then we will simply multiply this charge q naught with the potential, and we will get the potential energy or work done. So now first we will find the potential at point E due to the charges on the vertices. Remember, this is not present yet. Simply we are going to find the potentials only. Now we know the formula for the potential. It is V is equal to K Q by distance R, where K is equal to 1 upon 4 pi epsilon naught. So at this point, the potential due to this charge at distance r will be this much. Here we have taken this distance r for simplicity. Second, the potential at this point due to this charge, which is negative, so that potential will be minus. You can see here the magnitude of the charge is same, but one is positive and the other is negative. For positive charge, the potential is positive, but for negative charge, the potential will be negative. So, we can say that here the potential, one is positive, the other is negative, and so they will cancel out. Result will be 0. Again, at this point, the potential is due to this charge also. Again, the distance is r, charge is plus q, so potential is positive. While at last point, that is point D, the potential here will be negative because the charge is negative. So once again, due to these two charge which are at point C and point D, the potential at the center will be 0. And so the potential at point E due to all these charged particles which are on the vertex is 0. And if the potential is 0, and if we multiply any charge q with this potential, then the result will be 0. And we know that q into v is nothing but potential energy, and that is equal to work done. Now finally, look at the mathematical steps. Potential at point E, that is center, is the summation of the potentials of all the charges. We have given this equation number 1. Now the potential at A and C will be same because they are having positive charges, and so V1 is equal to V3 is equal to KQ by R. Also, the potential of B and D is same, that is V2 is equal to V4, but as here the charges are negative, so the potential is negative. Now here we have taken the distance of center from the vertex as r, but actually r is not given in the data. We have taken it for the simplicity. In the data, the side of the square is given, which is equal to d. So we need to mention that what is r. So r is equal to d upon root 2. How it is obtained? That is quite simple. You can see from the figure. So now if we'll put these values in equation 1, then the resultant potential will be 0, as I explained earlier. And finally, what is the work done? So work done is equal to Q into V. But as V is 0, so 0 into anything will be 0.